And I'm going to start sharing my screen. And when I first share my screen, I'd like to start looking at the home page. Hopefully everybody got from me. Oh, did I not send it to this class? The email announcement about tutoring being available through the Academic Center for Excellence. And so if you want to sign up for tutoring, they do have tutors available for this course. You can sign up for a regular time slot. You can that would meet weekly. You can sign up for tutoring just once. It starts next week. It will be available both through Zoom, and it'll also be available in person if you have the opportunity to get to the Learning Commons. I think they might also be having some tutoring on a drop-in basis too. But if you need extra help, you can go to the ACE. Also, again, I'd like to encourage people to make use of my office hour. I did create a separate link in Blackboard as we're looking at Blackboard on that left-hand toolbar. Underneath course information and syllabus, way at the bottom below your grade, there is a link there that gives the times for my office hours: Monday, Wednesday, Friday at 9, Tuesday and Thursday at 11. And if you click on that link, pardon me, it'll take you right to the Zoom room where my office hour is. And so you can just click right there during those times to get to my office hour. If you want to meet with me one-on-one for anything outside of class time, please feel free to send me an email. And if we can set up an agreeable time, that would be the link that you would also use. Separate question, would it make your folks easier if in this list, I also put a link for the class meeting so that you can just go to Blackboard and click on something here to get into the Zoom class?
Definitely.
Okay, I will try to get that done before Friday. So that having been said, next, my math lab. How is everybody doing? Has everybody gotten into my math lab? Hasn't if anybody's had difficulties getting into my math lab, can I ask you to please stay for a minute at the end of class and I can work with you one-on-one with whatever difficulties you might be having. When I looked this morning, most of you are in my math lab, but not everybody. Realize that quiz on Friday is in my math lab. So if there's something up and you're not getting in there by Friday, you've got to talk to me. That first homework is due on Friday. That's section P1. Has everybody gotten started with that? Does anybody have questions on any of those problems?
No.
No? Okay, all right. I'm going to go back and look at a couple of those problems in a minute. I'm turning now to the sort of announcements for the day and where we're going to be taking notes. Today we're going to look a little bit at writing expressions. We looked at pretty much everything to do with expressions last class, but we didn't actually go through that idea of writing expressions, which was the idea of converting a sentence into an expression. And then we're going to start looking at exponents. Homework P1 is due on Friday. The quiz will be on questions like what's in homework P1. Homework P2 will be due on Wednesday, and that's the section on exponents that we'll start looking at today. So, looking at writing expressions. I'm hoping that a bit of this content is familiar to you from previous algebra classes. In terms of writing expressions, we want to translate words into an expression. And we're going to make a little bit of a list, not too comprehensive, But let's see what we can come up with. Where there are some keywords that you're going to have to tell you what operations to use. And keywords for addition might be if you see the word sum, might be if the word you see total, might be if you see the words more than. Can anybody think of any words, other words that might tell you when you're changing a sentence to an expression that you would be using addition? And? Great. I'm sure there's more to the list, but I think that's a good start. How about subtraction keywords? Can anybody think of any words that would tell you to subtract?
From.
Less than.
Less than?
Difference.
Beautiful. Difference. Minus. So, again, there's probably more that we could add to that list, but can anybody think of anything else right now? If not, how about multiplication?
Product.
Beautiful. Anything else? Pardon?
Times.
Times. Does anybody see the word of mean multiplication? I go to the store and I buy 2 of something. I multiply the price by 2. Also, if I'm taking, let's say, 50% of something, that means I'm going to take that 50% as a decimal and multiply it. That word of will also tell us to multiply. And how about division? Quotient?
How many times?
How many times? If we're looking for how many times we divide to find it, undoing multiplication. Also the idea of ratio. If we're taking the ratio of 2 things, we're setting them up in a fraction, which means that we'll divide. So, initially I wasn't going to go there, but then with the other section yesterday I did, because I remember in previous semesters, there were some people who said that they sometimes struggle with turning expressions into words. So I'd like to look at just a couple of examples from the homework. And so once it comes up, let's look at, let's say, question number 34. And 34, is that font large enough for you folks to read? It says, asks you to write the English phrase as an algebraic expression and then simplify it. They tell you to let X represent the number. The phrase that we have is a number. Okay, so that's our X. Decreased by. If I'm decreasing, what operation do you think we should use?
Subtraction.
Subtraction. And over here, it's being decreased not by a single quantity, but by a sum. And to show that we're decreasing by a sum, we're going to have to use parentheses. And a sum means add. So does the need for parentheses there make sense to everybody?
Yep.
Okay. And so then sum means add the number and 1. And so first blank, they ask you to put that without simplifying. And then after that, they ask you to simplify. And again, that process of simplification is what we were going over last class. And we had said that if there's a subtraction in front, we're going to put a 1 and distribute. Distributing that -1 gives me negative x minus 1. And so the simplified version would be -1. And so that idea of taking that sentence and turning it into the expression. Is that all right for everybody? There's a few of those in the homework, and there's one on that quiz that's coming. If that's okay, I'm going to turn my finger back into a mouse, clear that, and go back to the notes. And then the next thing that we need for these last questions is the idea of what makes something an equation. And is everybody familiar with what's the difference between an expression and an equation? Anybody have an idea what's the difference between an expression and an equation?
An equation has an equal sign.
Beautiful. An equation contains an equal sign. So an equation sets two expressions equal. And in this homework, there's one particular type of equation that you'll be asked to use, and that's a formula. And a formula is an equation that shows the relationship between variables. And so an example of a formula might be something like F equals 9/5 C plus 32. Has anybody seen that formula before? Does it look at all familiar to anybody?
Isn't that converting Fahrenheit to Celsius?
Beautiful. So that F is the Fahrenheit temperature and C is the Celsius temperature. And so I might use that to find the degrees Fahrenheit if the temperature is, let's say, 15 degrees Celsius. And is everybody all right? In order to do this, we're going to just substitute 15 for Celsius, giving me F equals 9/5 times the Celsius temperature is 15 plus 32, then simplify. And so hopefully everybody remembers to multiply a fraction by a constant. I'll put it over 1. And again, I'm kind of old school. I do this by hand as opposed to using a calculator. And I reduce. 5 goes into 15 3 times. 9 times 3 is 27. Plus 32 gives me 59 degrees Fahrenheit. And are questions like that all right for everybody? Going back to that homework, one that is a little bit like this, but has a bit more involved, would be in that same assignment, question number 38. And so let's take a quick look at that. If this lets me open it. Is it doing anything? Well, I did want to look at question number 38, but I think that my labs doesn't want me to. Oh, no, it does. Here we go. Here we've got the formula. Excuse me. The formula T equals 26 x squared plus 823x plus 15,037 models the average cost of the tuition and fees T at a private college for the school year ending X years after 2000. The graph to the right shows the average cost of tuition and fees at private four-year college. Use the formula to find the average cost of tuition and fees at private colleges for the school year ending in 2010. And so over here, looking at this, is everybody all right? Well, no, I don't want to use that marker. In 2010, well, that would be 10 years after 2000, so we'd substitute in x equals 10. And so that would give me 26 times 10 squared plus 823 times 10 plus 15,037. And my pen doesn't want to write on this. It doesn't want to give me curves. I apologize. Is everybody all right then simplifying that to get the result? After you do that, there's a part B that asks you to find that tuition based on the graph. And is everybody all right that based on the graph, in 2010, it would be 25,825. And then part C would ask you to compare your two answers. Is the general idea of this question okay for everybody?
Yes.
Not hearing any concerns, I'm going to clear it and get out of my labs and then pick up from where we left off with those notes. That's the end of section P1. And so we're going to switch and start looking at section P2. And I guess rather than doing one long drawn out page for notes, let me add a page and we'll start section P2. Deals with exponents. And so looking at exponents, the first thing that we want to do is define. And so if I have something that's written like B to the n, over here, is everybody familiar with the idea that B is considered the base and that superscript after the quantity B is called the exponent. And it means that I'm going to take that quantity B and multiply it n times. And that's the definition if n is a natural number, a counting number. So if n is a natural number, b to the n is the product of n factors of b. And so, for example, if I take something like -2 to the 5th, and again, I think first day of class, we discussed the importance of parentheses in doing computation like this. We're taking -2 and multiplying it by itself 5 times. And I think first day of class, for those of you who are using a calculator, we had said to evaluate this, you'd open parentheses, -2, close parentheses. Then for exponents, I think most of you on your calculators will have that caret up button. If you don't have that caret up button, you might have a button x to the y, or you might have a button y to the x. Then we type in that exponent 5, and when we hit equals, or when we do the multiplication that's called for here, what are you guys getting? Is anybody getting anything? -2 to the 5th. Not hearing anything. Did anybody get as a result -32?
Yeah, that's what I got.
Is there anybody who, using their own calculator, got something other than -32? Nobody got something crazy like 0.04, did they? Then, if we're all comfortable with that definition of exponents, we're going to look for, excuse me, rules for operations with exponential expressions. So rules for operations with exponents. Exponents show multiplication. And so for the first rule, what we're going to look at is the product rule. And I hope you folks can humor me for a minute. I know that when I was a student, if somebody just said, here's a rule, memorize it, I had that Teflon in memory, everything slid right off. But if somebody took the time to show me why something was that way, I was much more likely to remember it. And so I'd like to take a minute to show you why it works that way. This product rule only holds if I multiply quantities with the same base. And so let's look at an example. Let's look at something like if I have x to the 3rd times x to the 2nd. And in order to make sense of this, I'm going to be a little kid and bring these back to their definitions. X to the 3rd means I've got 3 x's that I'm multiplying. X to the 2nd means I've got 2 x's that I'm multiplying. And so when I multiply them all together, I'm multiplying 5 x's, so that would give me x to the 5th. And if your exponent is a natural number and you're a glutton for punishment, you could draw them out that way each time and count how many you're multiplying. But is it easy to see that if I take 3 x's and multiply them by 2 x's, I get 5? And that product rule says if I have x to the m times x to the n, I get x to the m plus n. Or if the bases are the same, to multiply, I add the exponents. And so another example, if I have something like y to the 8th times y to the 4th, my bases are the same. Whoops, I add exponents, and I forgot to add in here. We keep the base. The base does not change. So here, these both have a base of y. My product will have a base of y. And if I multiply 8 y's by 4 y's, altogether I'll be multiplying 8 plus 4, or 12 y's. So that would be y to the 12th. Does this look like familiar territory to everybody?
Yep.
So what if I have 3 times 3 to the 4th? They have the same base, but this first one does not have an exponent. Is everybody familiar with the idea that if there's no exponent written, it means I have an exponent of 1? And so this is taking 3 to the 1st times 3 to the 4th. And now examples like this, where the base is a constant, not a variable, is one of those places where students sometimes make a careless mistake. Remember, we said that if the bases are the same, the base has to stay the same. And so when I take 3 to the 1st times 3 to the 4th, I'm still going to have power of 3, but it'll be 3 to the 5th. And then either multiplying by hand or using a handy dandy calculator, when you take 3 to the 5th and multiply 3 times 3 times 3 times 3 times 3, I believe you get 243. Is everybody all right with that one? Remember that if the bases are the same, it has to stay the same. And last example that I'd like to look at, if I have y to the 2nd times x to the 4th, and I might multiply that, by x, y to the 5th. It's all multiplication, so I should be able to simplify that. But not everything has the same base. So this time I'm going to physically rearrange them. In order to physically rearrange them, we can think of using the associative property, moving those parentheses to regroup, and then using the commutative property to change order. But regrouping and changing order, is everybody all right if I write that as x to the 4th times x to the 1st times y to the 2nd times y to the 5th? Again, those associative properties letting me group the x's and y's together after the commutative property allows me to change order. And now with the x's, they have the same base. I'll keep it and add the exponents. So this first product is x to the 5th. And then with the y's, because they have the same base, I'll keep it. And to multiply, I'll add exponents. And yeah, I can add 2 plus 5 is 7. So my final answer would be x to the 5th times y to the 7th. And I can't simplify that further because my bases are not the same. Is that all familiar territory to all of you?
Yep.
Okay, great. I hope I'm not boring you. Is this helpful going through them slowly like this, or am I wasting your time?
Slow is good.
Slow is good. Okay, all right. Then after we find the product, the next rule that we get is the quotient rule. And again, this rule applies if I divide quantities with the same base. And again, I'd like to start with an example to sort of justify that rule to you. Let's say I have x to the 6th over x to the 2nd. X to the 6th divided by x to the 2nd. If I expand that x to the 6th, it means I have 6 factors of x in the numerator, or I'm multiplying 6 x's together. I have 2 factors of x in the denominator. And does everybody remember, in order to simplify a fraction, to reduce a fraction, I can divide both numerator and denominator by any common factors, which has the net effect of crossing the ones that match up out. So when I reduce that, what I'm left with is 4x's in the numerator, or x to the 4th. And so from that example, I'm going to generalize and say, in general, if I have x to the m over x to the n, it's going to be x to the m minus n, or I keep the base and I subtract. And remember, with subtraction, order matters. It's going to be the exponent of the numerator minus the exponent of the denominator. And is that all right, or did I go a little overboard with abbreviations? Can everybody read that as the exponent of the numerator minus the exponent of the denominator?
Yeah, we can.
Okay, great. So another example, if I have z to the 9th over z to the 4th, when I find that quotient, the bases are the same, so I'm going to keep it. And 9 minus 4 would be 5. Instead, if I have something like 2 to the 12th over 2 to the 8th, be careful here. We had said that the bases have to be the same, which they are, but remember the base stays the same. So I'm going to still keep that base of 2, and then 12 minus 8 would be 4, and 2 to the 4th, 2 times 2 times 2 times 2 is going to give me 16. Be careful, the bases have to be the same and they stay the same. And when I subtract, it's the exponent of the numerator minus the exponent of the denominator. That one all right? Not hearing any complaints? What the quotient rule allows us to do is to expand our horizons, because our definition of an exponent was only defined for natural numbers. Let's first look and see what happens when we change that definition to one for whole numbers. And to define whole numbers, we'd have to define what it means to have a 0 exponent. And again, if you don't mind, I'd like to go through and use an example to show you where this definition comes from. Let's say I have a fraction x squared over x squared. At its most basic, does everybody remember that if I divide something by itself, and any quantity divided by itself will always equal 1. Any fraction where the numerator and the denominator are the same, if it's defined, will be equal to 1. But with what we just did with that quotient rule, we said in order to evaluate this, I can subtract exponents, and that gives me x to the 0. And so we're going to say that any base to the 0 power is equal to 1. But I just lied when I said any base. There is an exception, and that exception is 0 to the 0. 0 to the 0 is going to be something that's undefined. And because while logically we can show that anything to the 0 power should equal 1, over here this would have no meaning if I had 0 over 0, because I can't have 0 in the denominator. And likewise, there's a zero multiplication property that says if I'm multiplying with 0, it's got to equal 0, not 1. And so the two concepts conflict with each other. And the workaround is to say that 0 to the 0 has no meaning. It's undefined. So if I look at two examples, with these again, as with everything we've mentioned this semester, always keep in the back of your mind that order of operations. So let's say, for example, I have something like negative 1,287 x to the fourth, y to the fifth, z, in parentheses, all being raised to the 0 power. Well, everything in the parentheses is being raised to the 0 power. As long as I'm sure that none of my variables are equal to 0, this is a single quantity to the 0 power, so it'll equal 1. Next example is going to be a little bit different. Next example, let's say I have negative 3x to the 0. In this one, does everybody notice that there are no parentheses? Since there are no parentheses, using my order of operations, I have to do the exponent first. And so this becomes negative 3 times x to the 0 is 1. And so my final answer here would be negative 3. And again, this is because based on that order of operations, I do the exponent first. And so the variable to the 0 power is 1. And so this is negative 3 times 1, or negative 3. So again, be careful, remember that order of operations. So now we've gone from natural number exponents to whole number exponents. Next big leap of faith, we're going to look at integer exponents. And when I add the integers, what I have to be able to define is what it means to have a negative exponent. And in order to try to give definition to a negative exponent, I like to go back to that quotient rule. So let's make ourselves a fraction. Let's put x in the numerator and the denominator. Let's put exponents on them. But this time, let's make sure that the exponent in the numerator is smaller than the exponent in the denominator. If I go through and draw this out, it means I have 2 factors of x in the numerator, 5 factors of x in the denominator. And when I divide out common factors, in the numerator, I'd be left with 1. And in the denominator, I'd be left with 3 factors of x. So that would give me 1 over x to the third. But if I tried to use that quotient rule, I would have x to the 2 minus 5, or x to the negative third. And so since these both started with the same place, I'm going to say that x to the negative third is 1 over x to the third. And so in general, if I have a negative exponent, it's going to mean that I'm going to take 1 over something to the positive power. So it's the reciprocal of that quantity to the positive power. So for example, if I have y to the negative fourth, that will be 1 over y to the fourth. And in this section of the homework, you're going to see a lot of the directions tell you to write the expression using only positive exponents. or write without negative exponents. Another example, I might have something like x to the second times y to the negative fifth. That would be x to the second. And here, if I want to write that with a positive exponent, I need the reciprocal. So that's 1 over y to the fifth. And so if I think of putting that x over 1 so that I can multiply that quantity by the fraction, my final result is x to the second over y to the fifth. Or the shortcut that goes through my mind without doing that middle step is I realize that if I have negative exponents, it means I'm going to probably have a fraction. Any factor with a positive exponent, that exponent remains positive in the numerator. Any factor with a negative exponent, that exponent will become positive in the denominator. So positive exponents stay put in the numerator. Negative exponents move to the denominator. But then they can also get a little dicier than that. I could have something instead like x over y to the negative second. And so x has a positive exponent. Y to the negative second, well, we said that means 1 over y squared. And oh dear, now I have this horrible looking complex fraction. Hopefully everybody remembers that a fraction represents division. So that would be x divided by 1 over y squared. And then you guys remember to divide by a fraction, you might have heard keep, change, flip. Or to divide by a fraction, you multiply by the reciprocal. And so here my final answer would be xy squared. And so if I have an expression with a negative exponent in the denominator, that exponent will become positive when I move it to the numerator. Likewise, if I have an expression with a negative exponent in the numerator, that exponent will become positive when I move it to the denominator.
Wait, why did you multiply it though?
If I had, I'm going to do scrap work down at the bottom of the page. If I had something like 4 divided by a half, do you remember in order to divide by a fraction, you keep the first the same, the division becomes multiplication, and then you take the reciprocal, that idea of keep, change, flip.
Oh, okay, I remember now.
Okay, all right. It's easier to remember when you see it with numbers than letters. Thank you very much for asking me to clarify. So negative exponent means take the reciprocal, move the part of the fraction that you're in. Another example, if I have x over y to the negative second, that negative exponent means take the reciprocal. And so I can think of that as y over x to the positive second. And last one that I'd like to look at. No, I lied. It's not quite the last one. There's a couple more. If I have something like 10 to the negative third, hopefully this reminds you of scientific notation. Does everybody remember? If I have something like 10 to the negative third, that means if that exponent is negative, I'm going to have a decimal, because by definition, that's 1 over 10 to the third, which would be 1 over 1,000 or 0.001. that idea that I have 3 places behind the decimal point. Couple more. What if I ask you to write without negative exponents, something like x to the second, y to the negative third, z to the negative fourth? I can't combine any of these because they're all different variables. The factor that has a positive exponent, I'm going to have it stay put because I want to express it with positive exponents. Where I have that negative exponent in the numerator, remember I'm going to take the reciprocal, which means move that factor to the denominator in order to make that exponent positive. And in the same way, where I have a negative exponent in the denominator, taking the reciprocal of that factor would move it to the numerator to make that exponent positive. Okie dokie. Two more. And they make use of a combination of what we've done so far. If I have xy to the second times x to the negative fourth, y to the third, there's a couple of different approaches that you can take with a question like this. I'm going to first say, okay, all right, so I'm multiplying, so I'm going to use my product rules. I'll multiply the x's. This first x has an exponent of 1. When I multiply, I add exponents. 1 plus negative 4 will be negative 3. And in the same way, I'll keep that base of y. And when I multiply, I add exponents. 2 plus 3 is 5. To that point, is everybody okay?
Yep.
But now we want to write that without negative exponents. And since there is a negative exponent, I'll create a fraction. If something has a positive exponent, it will stay positive in the numerator. And if something has a negative exponent, I have to take the reciprocal. And so that exponent will be positive in the denominator. And last exponent that I'd look at that focuses on this definition of negative exponents is, what if I have a quotient? What if I have something like y to the fourth z over y z to the negative second? Well, let's see, this y that doesn't have an exponent really has an exponent of 1. This z that doesn't have an exponent really has an exponent of 1. And does everybody see this as a division problem? And we had said quotient rule, when I divide on the same base, I'm going to keep the base and subtract the exponents. So that'll be y to the 4 minus 1. And likewise, it'll be z to the 1 minus negative 2. And 4 minus 1 is 3. And 1 minus negative 2, when I subtract a negative, I add the positive, so that becomes 3. And so that would be my final answer. And so those operation rules that we have for multiplication and division will hold true. To multiply, we add exponents. To divide, we subtract exponents. And while we started looking at those rules with the definition of only having a natural number exponent, we'll find that those rules hold true for any exponent. positive, negative, 0 included. And those of you who are on this math train all the way through calculus, once you start being able to manipulate expressions with exponents, it will make calculus a hell of a lot easier. So, but I digress. Quotient rule, all right, with all its variations, 0 exponent, negative exponent. If so, next rule that we're going to look at is a power rule. And the power rule gets used oh, I skipped a row. We'll go back and get that other one. If I raise a power to a power, and again, I'm going to work this out for you. If I start with something like x to the 4th to the 3rd, at its most basic, doesn't that mean x to the 4th times x to the 4th times x to the 4th? And so doesn't that mean I'm taking 4 x's and multiplying it by 4 x's and multiplying it by 4 x's? And so when I add up all together, I'll have 12 x's. Or using the product rule, 4 plus 4 plus 4 is 12. But if I put the starting piece next to the final piece, doesn't it make sense that, well, if I have 3 groups of 4, I have 3 times 4, or 12 x's. Or if I raise something with a power to a power, I multiply the exponents and keep the base the same. So if I raise a power to a power, I multiply those exponents, but I keep my base the same. So a couple quick examples. If I have z to the 5th to the 6th, well, if I have 6 groups of 5, that'll give me z to the 5 times 6, or z to the 30th. If I have something like x to the 2nd to the negative 4th, well, that means I have, negative 4 groups of 2. Well, power rule says I'm going to multiply 2 times negative 4, which will give me x to the negative 8. And if the directions tell me not to use negative exponents or to express it with a positive exponent, it'll be, oops, it won't be 1 over 8, I apologize. It'll be 1 over x to the 8th. Let's say my base is a number. Let's say I have 2 to the negative 2nd, and I'm raising that to the negative 3rd. Exponentiating first, when I raise a power to a power, I keep the base and I multiply my exponents. Negative 2 times negative 3 would be positive 6. And then if I were asked to evaluate that, 2 times 2 times 2 times 2 times 2 times 2 would give me, I apologize, 64. Those okay? If I raise a power to a power, I keep my base and multiply my exponents. Next rule then deals with if I raise a product to a power, and so if I look at something like xy in parentheses to the third, well, that means xy times xy times xy. And when I rearrange, I'd have three factors of x multiplied by three factors of y. And so in general, if I raise a product to a power, I raise each factor to that power. And so looking at more examples, if I have something like in parentheses 2x to the third to the fourth, because I have parentheses and it's multiplication in there. Again, this only holds if I have a product, if I'm multiplying. If there were any other operation in there besides multiplication, it would be a very different problem. But because it's on multiplication, I'm going to take each factor and raise it to that outside power. So that'll be 2 to the fourth times x to the third to the fourth. 2 to the fourth, when I evaluate, will give me 16. And here, x to the third to the fourth, or when we raise a power to a power, we multiply those exponents. Instead, that same rule is going to hold true if those exponents are positive or negative. Let's say I have something like 3x to the fifth, y to the negative second, z, all being raised to the negative second. Well, if I'm raising this entire thing, and is everybody all right? It's all multiplication in there. So it's a product that I'm raising to that power. It means I need to raise each factor to that power. In doing that, for a minute, I'm going to leave that 3 to the negative second. Here, when I raise a power to a power, I multiply those exponents, x to the negative 10. Here, when I raise a power to a power, I multiply those exponents, y to the positive 4, and then I'd have z to the negative second. Now, if I'm asked to write that without a negative exponent, I need to remember to make a fraction. Any factor with a positive exponent, that exponent will stay positive. If I put it in the numerator, any factor with a negative exponent, that exponent will become positive when I move that factor to the denominator. And so my final answer would look something like y to the fourth over 9x to the 10th z squared. How do those ones look? If there are no questions, let's then next look at what happens when I raise a quotient to a power. And so let's say I have x over y to a power. What I'm going to end up doing is raising the exponent to that power. I'm sorry, raising the denominator to that power and the numerator to that power. I raise both parts of the fraction to the power. And so, for example, if I have something x to the fourth over y to the negative second, all being raised to the negative fifth power. To raise that fraction to a power, I'm going to raise the numerator to the negative fifth. Then I'm going to raise the denominator to the negative fifth. When I raise a power to a power, I'm going to multiply those exponents, giving me x to the negative 20th over y to the positive 10th. And then to express that without negative exponents, anything with a positive exponent is going to stay where it is. Anything with a negative exponent will become positive when I move it to the other part of the fraction. And here, because there's nothing left in the numerator, we'll put a 1. So my final answer would be 1 over y to the 10th x to the 20th. So, that having been said, I am going to give you folks 5 problems to do. I'm going to wait about 5 minutes, have you work on them, and ask you to tell me what you get. So practice. Did you guys want to work alone on these, or did you want to work in groups?
I prefer alone.
You prefer alone. I see how it is. Someday people will say, oh, she was always a nice girl, but she seemed like a loner, right?
I'm a definite introvert for sure.
Okay, so let's look at 2x to the negative third yz to the negative fourth times 2x to the negative fifth. And in each of these, please write your final answer with only positive exponents. Let's look at negative 5 x to the fourth y times negative 6 x to the seventh y to the 11th. Let's look at negative 3 x to the fourth y to the sixth, all being raised to the third. Let's look at 3x to the fourth over y, all being raised to the negative second. And lastly, let's have you guys try x to the fourth, y to the fifth, z to the sixth over x to the negative fourth, y to the negative fifth, z to the negative sixth, all being raised to the negative fourth power. What fun. So I'll check on you guys in about 5 minutes. If you get stuck, either ask for help or go on to the next one, and we'll go over them all in a couple. How did I do with the first one? With the first one, could everybody get 4y over x to the 8th z to the 4th?
Yeah.
Here, starting with multiplication, I add the exponents, and then I rewrite the negative exponents as being positive on the opposite side of the fraction. Next one, multiplying, realize the negative coefficient has absolutely nothing to do with what the exponents. Negative coefficients, the product there is 30. On the x's, I add the exponents. On the y's, I add the exponents. So that'll be my final answer. Did everybody get 30x to the 11th, y to the 12th?
Yep.
Third one, I have to raise each factor to the third power, -3 to the third, x to the 4th to the third, y to the 6th to the third. When I evaluate, gives me -27, x to the 12th, y to the 18th. Next one, there's a couple of different approaches that you can take, depending on whether you see the glass as half empty or half full. I'm going to do this one twice. One approach is to say, okay, I've got to raise everything in the parentheses to the -2nd. So that's 3 to the -2nd, x to the 4th to the -2nd, over y to the -2nd. Gives me 3 to the -2nd, x to the -8th, over y to the -2nd. And then I'm going to move things so that they have positive exponents, giving me y squared over 9x to the 8th. Option 2, which some people find easier, is to remember that if I'm raising a fraction to a negative power, I'm raising the reciprocal to the positive power. And so that would take me to y to the 2nd over 3 to the 2nd, x to the 8th, or y squared over 9x to the 8th. There, it's interchangeable which we do first, because order of operations say exponents first, and they're both different ways of manipulating those exponents. Last one, let's see if I can get a little tricky here because I didn't leave enough room for my work. Whoa, how fancy was that? Again, two different approaches depending on whether I see the glass as half empty or half full. One approach, I'm going to simplify what's inside the parentheses first and do my division by subtracting exponents, giving me x to the 8th, y to the 10th, z to the 12th, all being raised to the -4th. And then raising each factor to that power, it's x to the 8 times -4, -32, y to the 10 times -4, -40, z to the 12 times -4, -48. And then because they're all negative, they'll be in the denominator. Does that work for everybody, or did you want to see that worked out other ways? We okay?
Yep.
How'd you guys do?
Silly mistake.
Terrible.
Terrible? Going over them, can you see what you missed, what you should have seen?
Yeah.
Okay, now I am guessing, I'm going to stop sharing my screen. One thing that I hear repeatedly is, wow, when we do it together in class, it looks so good. It looks so, I can do that. But when I try it on my own, and that's the purpose for homework, for you to have that opportunity to try it on your own. So please start looking at these. Again, these exponent problems are what is in that homework P2. And there's more in that homework problem for section P2. But try, in addition to tying up with the loose ends on that assignment P1. Try looking at that as the first part of that assignment P2. Does anybody have any questions that they are pressing right now? And is there anybody who came in after I took attendance? If not, have a great day, or if you want to talk to me, stick around, especially if you're having problems with my labs. Is there anybody who came in late that I didn't get?
Oh, I think it came in late.
Okay, you know what? I believe I saw you in the waiting room, so I got you. Thank you for making sure. Anybody else?
Hi, yeah, I had myself muted during attendance, so I didn't say my name, or I didn't say I was here.
I saw your little box, so I got you. Thank you.
Okay, thank you so much.
Thanks for checking. Great.
I came in a couple minutes late for attendance.
Okay. Thank you, Carissa. I did not get you because at that point in time we were already teaching, so I didn't stop to add you. Thanks a lot. Anybody else?
Here, ma'am, I also have one question.
Sure.
For the homework, like, I already did it without like coming to class, so like I made some mistakes. So I don't know if I could take it over.
In my math lab, you have infinite do-overs on the homework. You can keep going back in there and doing the problems again and again until you get them right. When you look at a problem that you got wrong, they give you 3 tries before they say it's fully wrong. After those 3 tries, there's a place where you can go try a similar exercise. And it's not the same problem, but it's a similar problem. So you can go through and redo it again and again and again until you get them right.
Okay, thank you very much.
Okay, thanks for asking. I'm glad you're concerned enough to want to go through and change them. Great. Anybody else have anything? Jennifer, are you there? Any questions?
Yeah, I'm good. Thank you.
Okay. Cameron, are you there? Any questions? Jakaya, you're good? Okay, Steph, Carissa, any questions? If not, I'm going to end class, you guys. Have a great day. We'll see you on Friday.
You
Or
too.
December. Okay, bye-bye.